So in this video, we are going to use Bazoot's identity, which is a result in number theory, to understand which elements inside the ring of integers modulo n have multiplicative inverses. So Bazoot's identity is absolutely crucial prerequisite knowledge to be able to watch and understand what we do in this video. So if you aren't familiar with that result, please go to my playlist on number theory, and in that playlist there is a video on Bazoot's identity. Please watch that video before returning to this video. We proved the Bazoot's identity in that video. So going forth, I will assume that everyone is familiar with that result. So we're going to be talking about the ring of integers modulo n, which I will denote Zn. And we're not going to pick a specific n. What we're going to say is going to apply for all of them. So remember, this as a set is a finite set, and it will contain the elements 0, 1, 2, all the way up to n minus 1. And this set will have two composition laws defined on it, an addition composition law and a multiplication composition law. And remember, the way those composition laws are defined is you think about each of these elements as representing a congruence class modulo n in the larger ring of integers. And then if you want to know what any two elements added together or any two elements multiplied together is, you think about going to their congruence classes, picking representatives out of them, adding those representatives together, or multiplying those representatives together if we're talking about multiplication, in the integers. You'll get some answer in the integers, and then you just ask what congruence class is that answer in, and then that congruence class will be represented by something back over here, and that will be the answer to what your two elements added or multiplied together is equal to in our integers modulo n number system. So what we're interested in this video is which elements inside the ring of integers modulo n have multiplicative inverses. So if I take an element inside here, let's call it x. So x is an element inside Zn. How do I know whether or not this element has a multiplicative inverse? So I'm going to give you the answer, and then I'm going to explain why this is true. So x inside Zn will have a multiplicative inverse inside Zn if and only if it is coprime with the number n where you're viewing both of them as integers. So of course n isn't an element inside your finite number system, so you have to step out of that back to the number system that we know and love, the integers, and we know what greatest common divisor means in that context. So if the greatest common divisor of x and n is 1, i.e. they are coprime, then and only then will x have a multiplicative inverse in the ring of integers modulo n. So we need the greatest common divisor of n and x to equal 1, and fancy bit of notation or fancy name for that is the two numbers n and x are coprime to one another. So I'm going to firstly prove that if this is the case, then x will definitely have a multiplicative inverse, and then what I'll show you is that if this isn't the case, i.e. if their greatest common divisor is some number bigger than 1, say 2 or above, then x won't have a multiplicative inverse in this ring. So this first bit is where we're going to use Bazoot's identity. So firstly, I'll just remind you of what Bazoot's identity says, but we're not going to prove it in this video. As I say, if you want the proof, go to the video on Bazoot's identity. So Bazoot's identity says that if you have two integers, n and m, and the greatest common divisor of these two integers is equal to some value, let's call it d, then Bazoot's identity gives you an equation that holds true in the ring of integers. It says that there are two integers that you can find. There exist z1 and z2 inside the integers such that this equation holds true as an equation in the integers. So z1 times n plus z2 times m is equal to d. So what this is saying is it's possible to find a multiple of n and a multiple of m such that if you add them together, the sum is the value of the greatest common divisor of n and m. There are two integers that make this work as an equation in the ring of integers. Now, we're going to apply this result here, and indeed Bazoot's identity, actually, just another little interesting fact, gives you a way of actually finding these integers, z1 and z2. You can use the extended Euclidean algorithm to find these two. So, we're going to apply Bazoot's identity to what we've got here, the fact that the greatest common divisor of n and x is equal to 1. So what it tells us is that as an equation in the integers, there exists a z1 and a z2, such that z1 times n plus z2 times x is equal to 1. Now, how does this help us? Because this is just an equation in the integers. We want to use this to infer something about what's happening in the integers modulo n. Well, what we can consider is, well, firstly, let's just rearrange this. We're very interested in this part because we've got something times x, something in the integers times x is equal to 1. And then if we move this bit to the other side, we'll have is equal to 1 minus z1 times n. So z2 times x is equal to this. But this is going to be something inside the congruence class of 1 because it's 1 plus, and then let's swallow that minus 1 into the z1 here. So we'll have 1 plus, and then we've got minus z1 times n. z1 is an integer, so minus z1 is an integer. So we've got 1 plus some integer times n. That is something that's going to be in the congruence class of 1. Remember, 1's congruence class, which we could denote 1 bar, or we could denote square brackets 1, or we could denote square brackets 1. If we were being really formal, we'd subscript it n, is all the elements from the integers that are of this form, 1 plus z times n, where z is allowed to vary over the entire integers. So you'd have 1 plus 0 lots of n, so you just have 1. You'd have 1 plus 1 lot of n, 1 plus 2 lots of n, 1 plus 3 lots of n, 1 plus 4 lots of n, and then all the negatives as well, 1 minus n, 1 minus 2n, 1 minus 3n. All of them are going to be inside the congruence class of 1. And this thing is going to be one of those elements, because minus z1 is some integer, so it's going to be something inside the congruence class of 1. And this is incredibly hopeful because we've got something times x is giving you something that's inside the congruence class of 1. So if this thing was inside here, then if we multiplied the two of them together inside here, it would be giving us 1 as the answer, because the answer in the integers is something that's inside the congruence class of 1. Now, the one little problem is that z2 might not necessarily be inside here. However, we can get around that because z2 is guaranteed to be in some congruence class at modulo n. So it's going to be in the congruence class of one of these elements. And when you multiply two things together, using the congruence classes, we know that it's well defined, so it doesn't matter what representative you pick. So if we can find something that's in the same congruence class as z2, that is in here, and we'll be able to do that, then that thing times x must give you something that's in this same congruence class as what z2 times x gives you, i.e. it will give you something that's in the congruence class of 1. So let's go through this more slowly and write some of this down. So what we can say from this equation up here is that z2 times x is giving you an element inside the congruence class of 1. Now, z2, the big problem is that z2 is just an integer. It's something in the integers, but it isn't necessarily one of these numbers that we've got in our integers modulo n. However, what we do know is that there must exist some element in here such that z2 is in its congruence class. Let's call that element y. So there must exist a y is an element of Zn such that z2 is an element of the congruence class of y, and that's because the congruence classes modulo n of all of these elements completely covers the entire integers. So just drawing a short picture to explain why that is the case, if we just draw the integer number line like so, so here's 0, let's say, and here is n, then the congruence class of 0 is all multiples of n, integer multiples of n, so you'd have n, 2n, negative n over here, and onwards, so you'd have negative 2n, 3n, etc. And then if we look at the congruence class of 1, it's all things of the form 1 plus zn, so it's going to have 1 plus n, 1 plus 2n, 1 minus n, etc. If we look at the congruence class of 2 in blue, it's all the things of the form 2 plus zn, so you'd have 2, 2 plus n, which is here, then you'd have 2 plus 2n, 2 minus n will be over here. And you can see that as you continue on from 0 here to n minus 1 here, if you go through all of their congruence classes, it's going to fill in all of these gaps so that the whole of the integers is covered. So wherever z2 is, and it might be, completely off this picture, maybe it's over here, it will be inside one of these congruence classes. So there will exist some y, maybe this one here, such that when you look at its congruence class, it contains z2. So that's what we're saying here. There is some element inside here such that z2 is within its congruence class. Now I claim that y is now the element inside the integers modulo n that is the inverse, the multiplicative inverse to x. And the reason being is that if you multiply y and x together, the way you do this is by going to their congruence classes. So you look at the congruence class of y and the congruence class of x, and you take representatives from those, and you could take the representative z2 from the congruence class of y, and you could take the representative x from the congruence class of x. You multiply these two together in the integers, and then you look at what congruence class is the answer in, and we've already said that the answer to that is in the congruence class of 1, and then you take that thing's, the thing in here whose congruence class you're in as the answer. So you're in, therefore, 1's congruence class, and therefore y times x is equal to 1, which means, therefore, that y is the multiplicative inverse of x, because that's the definition of the multiplicative inverse of x, that you multiply together to give 1. Both ways, of course, needs to be true, but that clearly is going to be true if we do it the other way round, x times y, then we can use the exact same argument. Pick z2 as your representative of the congruence class of y, pick x as your representative of the congruence class of x, and then multiply them together in the integers, and we know the integers are commutative, so you're still going to get the same answer, i.e. an element of the congruence class of 1. So xy is also going to equal 1. So we therefore know that y multiplied with x in our integers modulo n is going to give 1 both ways round, and therefore y is the multiplicative inverse of x. So that completes our proof then that if x and n are coprime to one another, then x will have a multiplicative inverse inside the ring of integers modulo n. And just before we move on, let me emphasize that the incredible thing about the ring of integers modulo n that makes all of this possible is the fact that addition and multiplication are well defined. So whatever two representatives you pick from the two congruence classes, so if we're, for instance, multiplying y and x, whatever representative you pick from the y congruence class and whatever representative you pick from the x congruence class, when you multiply the two representatives together in the integers, you'll get a different answer depending on which representatives you pick. However, the answer will always be in the same congruence class, so the answer of what the overall congruence class you're in remains the same. It is well defined, so that's obviously crucial to what we did here. So let's move on now. So we want to now look at the case where the greatest common divisor of x and n is not 1, so it's instead equal to some d, where d is strictly greater than 1. It is, of course, still an integer. And we want to see how, in this case, it cannot be possible for x to have a multiplicative inverse modulo n. So the way I'm going to disprove this is by contradiction. So we'll suppose, for the sake of contradiction, that it does have a multiplicative inverse. That would mean that there is some y inside Zn such that y times x is equal to 1. Now, think about what this means in terms of congruence classes. we could take the representative y from the congruence class y, we could take the representative x from the congruence class x, and then if you multiply them together in the integers, you must get something that's in the congruence class of 1 modulo n. That means it must be equal to 1 plus z times n, where z is some integer. That's what it means for y times x in the integers to be in the congruence class of 1. These are all the elements inside that congruence class of 1, so it must be equal to one of them, so it must be equal to something. There must be a z that makes this true. Now this is a problem because we can rewrite this as 1 is equal to y times x minus zn. That's a perfectly valid manipulation inside the integers. And what we know is that the greatest common divisor of x and n is equal to this value d that is greater than 1. So we know that d is a common divisor of x and n, so d divides x and d divides n. That means that x can be written as some multiple of d, some integer multiple of d, we'll call it m1 times d, and n can be written as some integer multiple of d, m2 of d. So m1 and m2 are both integers. And now we'll just put those into this equation and we're going to get some garbage. So 1 is equal to y, whatever that is, the thing that can't exist, times m1 times d minus z times m2 times d. Now just pull out that d and we get this is y times m1 minus z times m2 times d. Now this is an equation in the integers. Y is an integer. Remember, it was just some number inside Zn, so it was an integer. It was some number 0, 1, 2, all the way up to n minus 1. It was one of those, but it transferred across into the ring of integers. So then we multiplied it by another integer, then we subtracted off two other integers multiplied together. This is all algebraic operations inside the integers, so it's going to come out as some integer. So this is then saying that some integer times some number that is greater than 1, so some positive integer bigger than 1 is equal to 1. Well, that's nonsense. We know inside the ring of integers there are only two elements with multiplicative inverses, 1 and negative 1. All of those positive integers bigger than 1 do not have multiplicative inverses. If this was true, this thing would be the multiplicative inverse of d. You know, imagine d is 3. There is no integer that multiplies by 3 to give 1. You know, because if you multiply it by 0, you get 0. If you multiply it by any negative integer, you're going to go into the negatives. You're not going to be equal to 1. If you multiply it by 1, you get d. If you multiply it by 2, you get 2d. You know, these are all getting bigger and bigger. They're never going to come down somehow magically to 1. So this is nonsense. This can't be correct. And therefore, we go back to our initial assumption that there was some multiplicative inverse for x, and it must have been wrong. So therefore, we have proven that if the greatest common divisor of x and n is greater than 1, i.e. they're not coprime to one another, then x cannot possibly have a multiplicative inverse in the ring of integers modulo n. So it is the case that if they are coprime, then x will have a multiplicative inverse, and if they're not coprime, then it won't have a multiplicative inverse. So it will have a multiplicative inverse if and only if x and n are coprime to one another. Now, before we end, I would just like to do an example of applying this to an actual concrete example. So I'm just going to come up with some numbers. So we'll take 9 and 14. So we'll take the ring of integers modulo 14, and then I'm going to look at the number 9 inside there. So of course this is a set is 0, 1, 2, all the way up to 13 with its addition and multiplication composition laws on it. I'm going to be interested in this number 9, and I'm going to do more than just find the multiplicative inverse of 9. I'm going to actually solve an equation inside this number system. So let's say we have the equation 9 times x is equal to 2. That's a perfectly valid equation inside this number system. 9 times some value, so I'm asking can you find, are there any solutions to this? Is there any x inside this number system that satisfies this, such that 9 times that x is equal to 2? Well, if 9 has a multiplicative inverse inside here, we could solve this just by multiplying both sides by that multiplicative inverse. Then by the associativity of multiplication, we could multiply 9 with its multiplicative inverse to give 1, and then we get x is just equal to the multiplicative inverse of 9 times 2. So this is going to be the multiplicative inverse of 9, if it exists, times 2. And what I'm going to show you is that it does exist in this case, and I'm even going to find its multiplicative inverse using the extended Euclidean algorithm. So 9 and 14, the greatest common divisor of 9 and 14 is indeed 1. So they are going to be coprime. You know, you can write 9 as its prime factorization, which is 3 times 3, and 14 as its prime factorization, which is 2 times 7. So they are going to have no common factors. What we can now do is apply the extended Euclidean algorithm to find the coefficients in Bazoot's identity for 9 and 14, and that will yield us the multiplicative inverse of 9. So doing this, 14 is equal to 1 times 9 plus 5 is the first line of the Euclidean algorithm. Rewriting this, we'll have that 5 is equal to 1 times 14 minus 1 times 9. So I'm assuming you're familiar with how to perform the extended Euclidean algorithm. If you're not, it's in previous videos in the playlist on number theory. Next line, we'll have that 9 is equal to 1 times 5 plus 4. We'll rewrite this to 4 is equal to 1 times 9 minus 1 times 5. And then we don't like this because we want equations completely in terms of 14 and 9. At the moment we've got an equation in terms of 9 and 5, but that's okay. We can substitute this equation that we've got for 5 into here, and we'll then have an equation in terms of just 9s and 14s. So this is going to give, we'll have 1 times 9 and then minus 1 times minus 1 times 9. So that's going to give another 1. So we'll have 2 times 9 and then minus 1 times 14 overall. And let's just do a check of our calculation here. 2 times 9 is 18, minus 1 times 14 is indeed 4. Good. Let's continue on. Third line of the Euclidean algorithm is going to be 5 is equal to 1 times 4 plus 1, and then the final line will just be 4 is equal to 4 times 1. So indeed 1 is the greatest common divisor by the Euclidean algorithm here. But let's do the next line of the extended Euclidean algorithm. It will give 1 is equal to 5 minus 1 times 4. So now just substitute both of these equations that we've got for 5 and 4 in terms of 9 and 14, and we'll get an equation for 1 in terms of 9 and 14. So this gives us 1 is equal to, so substituting in 5's equation, we've got 1 times 14 minus 1 times 9. Putting in 4's equation, we'll get minus 1 times 2 times 9, so that will give plus minus 2 times 9. And then we'll have minus 1 times 14, which will be plus 1 times 14. So this overall comes out as 2 times 14 minus 3 times 9. And let's just check that. 2 times 14 is 28. 3 times 9 is 27. So 28 minus 27 is indeed equal to 1. So now this is Bazoot's identity. These are the coefficients. So one of the coefficients is 2 in front of 14, and one of the coefficients is minus 3 in front of 9. And we can now use this to find 9's multiplicative inverse, because looking at this, we've got minus 3 times 9 is equal to 1 minus 2 times 14. So it's saying if we multiply negative 3 by 9, we get something inside the congruence class of 1 modulo 14, and this is a problem because minus 3 isn't exactly in our integers modulo 14, so we just need to find what congruence class is it in. So thinking about the number line, so you've got 0 here, and I have drawn the continuous number line which usually represents the reals, but we'll just think about the integers here. We've got 14 here, got minus 14 here. When you go backwards to minus 1, that is in the same congruence class as 13. When you go to minus 2, that's in the same congruence class as 12. When you go to minus 3, that's in the same congruence class as 11. So Minus 3 is in the same congruence class as 11. So that means that if we multiply 11 by 9 inside here, it will give us 1. So 9 times 11. Oh, and by the way, something that I will just tell you, I've been writing this in this way. Notation that you will see people use when they are doing modular arithmetic is the old notation, but it's still commonly used. You will often see people writing this instead with the bigger equals. They'll put 3 lines instead, 9x, and they read this as congruent to, and then they even write in brackets modulo 14. This notation is very common. I don't like it as notation because it implies that this is a less good number system. It implies that it's not a number system in a way. It implies we're just talking about the integers with talking about congruences instead of actually treating this with respect as a number system in its own right. So I actually prefer to just write this and say we're working now in this finite number system and we want to solve this equation. But you often will see things like this written, 9x is congruent to 2 modulo 14, and you'll be asked to solve this congruence equation. But it is effectively just a number system in its own right, and we're solving an algebraic equation in this number system. But this notation was invented years before the advent of abstract algebra, and it is still in use. And you'll more commonly see that written even than this. Anyway, where were we? So 9 times 11, I was prompted to think about that because I was going to put in brackets here modulo 14. So we're doing 9 times 11 in our modular number system here. So the way that you could do that is you would take representatives from these two congruence classes, and we could take 9 and 11, multiply them together in the integers, and we'd get 99, and then we just need to figure out what congruence class that is in. But we know we're guaranteed to get this right because another thing in the congruence class of 9 is negative 3. Sorry, not in the congruence class of 9. In the congruence class of 11 is negative 3, and we know that if we multiply 9 with negative 3 in the integers, it gives us this thing, 1 minus 2 times 14, which is in the congruence class of 1. So because we know everything works and is well defined, we know we're guaranteed to get in that congruence class, but let's just check this. So 99, we just now need to multiply 14 by something. So let's try 14 times 5 firstly. This will give us 70. So then let's do 14 times 6, that will give us 84. 14 times 7 will give us the bang on number 98. So 14 times 7, sorry, not times 17. Let me cross that out. 14 times 7 is equal to 98. So adding 1 onto that, you get 99. So this is actually equal to 1 plus 7 times 14. So indeed, 9 times 11 gives us something that is in the congruence class of 1, modulo 14. So yes, this is all working, as we knew it must do, because with this other representative of that same congruence class, it was giving something inside 1's congruence class. So what we can now do, going back to our original equation, if we want to solve this equation, we now know what 9's multiplicative inverse is inside here. It's 11. So we can now multiply both sides by 11. This side multiplying by 11 will give 1, so it goes. So we then get that x is equal to 11 times 2. If we want to work out what that is, again, we take representatives from their congruence classes, so we'll just take 11 and 2, multiply them together in the integers, we get 22, and then we just need to ask what congruence class is that in. Well, 22 is equal to 14 plus 8, so it's therefore going to be in the same congruence class as 8. So the answer is x is equal to 8. So if you take 9 and multiply it with 8 inside here, you'll end up with 2. We can finally just check that. So 9 times 8, take the representatives in the integers, 9 and 8, multiply them together. Gosh, maths, what is 9 times 8? 9 times 9 is 81, so 9 times 8 is 72. And then we can use what we've got down here. We know that 14 times 5 is 70. So this is 14 times 5 plus 2. and therefore it's in the congruence class of 2. So the answer is 2 modulo 14. So it works all beautifully. So if an element is coprime to the n that the integers is modulo, then it will have a multiplicative inverse. If it is not, then it will not have a multiplicative inverse. And this is how you can find multiplicative inverses using the extended Euclidean algorithm, and how you can use them to solve these sorts of equations in modular number systems, sometimes called congruence equations.